हेलो एवरीवन, वेलकम टू गेट अकेडमी। गुड मॉर्निंग ऑल। कैसे हो आप लोग? पहले बताओ, ऑडियो वीडियो क्लियर आर नॉट? एक बार बता दीजिए। यस, गुड मॉर्निंग प्रतीक, अंकित, गुड मॉर्निंग। नायक, गुड मॉर्निंग। गुड मॉर्निंग एवरीवन। अश्विनी, गुड मॉर्निंग। यस, ओके, बता दीजिए ऑडियो वीडियो क्लियर। एक बार बता दो आप, सब कुछ क्लियर है क्या? नहीं? यस, ओके, थैंक यू अश्विन। Okay, so in our last class we had discussed about effect of the transformer, operation of the transformer with effect of winding resistance. So winding resistance is considered in a practical transformer. What will happen? So two undesirable consequences takes place. One is a copper losses and also voltage drop due to the resistance. Okay. So we have discussed that how do we transfer the resistance parameter from one side to another side. What is a referring? Okay, referring means the process of the transferring the resistance and reactance parameters from one side to another side of the transformer. So okay, so in this session I would like to discuss about operation of the transformer with effect of the leakage flux. So we know in case of ideal transformer, what will happen? There is no leakage flux in a ideal transformer, but practically leakage flux is present in the practical transformer. So whenever the leakage flux is considered in a practical transformer, what will happen? Okay, this is our discussion. Okay, अगर लीकेज फ्लक्स कंसीडर किया था ट्रांसफार्मर में, after that what will happen in the transformer? Okay, this is our discussion. All of you clear point? So there is a question like, so if leakage flux is a consider the leakage, the flux phi L, the is considered, okay, in practical transformer, so then what will happens? Okay, this is what will the happen in the transformer. Okay, in transformer here. So got it my point? Okay, this is our question. So if leakage flux is considered in a practical transformer, so what will happen here? So first we have a, before discussing this question, okay, पहले ये discuss करने से पहले हम क्या जानना चाहता हूँ, ये what is mean by leakage flux, okay, and what are the basic reason, okay, what is the reason to get the leakage flux, that is a originating point, so to produce the leakage flux in the transformer. And there is a one more flux here, so that is a mutual flux and leakage flux of the transformer. So what are the difference between the leakage flux and mutual flux of the transformers? So we have a questions in our mind, so that is a what is leakage flux? Okay, this is the leakage flux of transformers. How do we define the leakage flux? And next one, what is the reason? Okay, this is the reason. So to get the leakage flux in the transformer, to get phi L, so in transformer, this is also another possibility of the question in our mind. So next one, the what is the difference between, okay, difference between the leakage flux and the mutual flux. So these are some questions, okay, we will discuss about all these questions. So before discussing if the leakage flux is considered in a practical transformer, what will happen here? So first one, what is the mean by the leakage flux? Okay, so here we have a diagram. See here, this is the transformer core. Okay, transformer core part. Okay, and it has a two windings. Okay, आपके पास two windings है, AB winding and the CD winding. सो ए बी वाइंडिंग को सप्लाई कनेक्ट कर रहा है और सी डी वाइंडिंग को लोड कनेक्ट कर रहा है हम. सो क्या होगा अगर इधर सप्लाई कनेक्ट करने के बाद, सो व्हेनेवर ट्रांसफार्मर इज एक्साइटेड विद द एसी सप्लाई, द टाइम वेरिंग नेचर ऑफ द करंट passes to the winding, so which create the flux in the primary winding. So this flux also links in the secondary winding through transformer core. So according to the Faraday's laws of electromagnetic induction, EMF induces in the primary winding as well as EMF induces in the secondary winding. So A winding को AB winding हम इधर कनेक्ट कर रहा है, the supply is connected to the AB winding. So this is the single phase okay AC supply. So this supply voltage is a V1. Okay, suppose let us assume this current, okay, this no exciting current flows here, okay, this exciting current. So I naught, okay, in this case. So this exciting current, okay, passes, okay, like this, okay. So this is the current directions, okay, and here current entering position and this one is a current leaving position. So according to the right hand thumb rule, okay, according to the right hand side, so right hand thumb rule or screw rule. So then what will happen? So this according to the right hand thumb rule or screw rule. So if the orientation of the fingers indicate the flux direction, so these indicate the current direction. Okay, if fingers indicates current direction and thumb indicates the flux direction here. So that flux lines is in the upward direction. Okay, so that these flux lines are in upward directions. Suppose the flux produce, okay, in this coil. So this have represented with the green mark here. So this flux is a, okay, this is the direction of the flux, okay, like this. So flux lines are passing, all the flux lines, okay, this is a, which flux here? So this flux is the, okay, primary flux of the transformer phi 1, okay. So which is the responsible to induce the EMF in the E1 and the EMF induces in the secondary windings. All of it clear point. So next one, when the load is connected, what will happen? So when load is connected, what will happen? See here, some amount of the flux, okay, whenever load is connected here, I am connecting the load, so in the secondary side across the CD terminals. So when the load is connected, so load current passes to the winding, okay, this load current, and produces one more flux in the machine. So that flux is equal to, so N2 I2 divided by the reluctance of the core. Okay, this is the secondary flux. What is the direction of this secondary flux? So secondary flux exactly, okay, just assume here, okay, current entering. So this is the entering positions. Okay, this one is a entering position. So current entering and this is the leaving. So according to the current right hand thumb rule, okay, this is the direction of the phi 2. Okay, this direction is a, so which flux here? Okay, phi 2 amount of the flux. Now similarly, when load is connected, okay, this load is connected, so it draws some amount of the current from the source. All of it clear point? So it draws some amount of the current from the source to supply the power to the load. So this current is known as, okay, load component of the current. So this current also produces one more flux here. So that is a phi 1 dash. So that is a N1, okay, I1 dash. So divided by reluctance of the core. So what about this direction of the flux? Okay, it is also, okay, it is a, so this flux is a phi 1 dash. Okay, so ideally, so these two fluxes are equal and opposite, nullify each other. But practically what will happen? So this flux is a, how much amount of the flux? This one. Suppose this is a 99% of the pi 1 dash opposes 99% of the pi 2. So to satisfy the Lenz's law. So and cancelled each other. What about the remaining 1% of the flux here? So this 1% of the flux, the present in the only in the primary winding, okay, only in primary winding. So through air medium, okay, like this, okay, this is a so present in the primary winding through air. Now similarly 1% of the pi 2 present in the secondary winding, so through air, okay, through the air, not in the core. So this is a which flux here? So it is a phi L2 and this one is a phi L1. So these two are present in the air, okay, air medium, not in the core. So that how do we represent the leakage flux here? The leakage flux is the leakage flux is a load component of the flux. So which links either in the primary winding or in the secondary winding, but not links in both windings of the transformer. So if the flux links in the both winding, this one is a, so it is a mutual flux, okay, mutual flux of transformer. So if the flux links in the both winding, it is treated as a mutual flux. And flux links in the secondary, either primary winding or in the secondary winding, but not links in the both winding. So this type of flux is known as the leakage flux, okay. So which is not the responsible to induce the EMF in the primary winding as well as the secondary winding, okay. Thank you, Ashwini. We got it. What is the mean by leakage flux here? How do we define? So under loaded condition, that is the leakage flux is a, we can say that the leakage, the flux is load component of the flux, load component of flux, okay, which links either in primary winding okay, or secondary winding, but not links in both windings of the transformer, okay. So that is the meaning of the leakage flux. So therefore total leakage flux, okay, that is a total the leakage flux of the transformer. So that is equal to, okay, it is a phi L1, so plus, okay, phi L2 here, okay, pi L1 and pi L2. So where, what is the mean by pi L1 here? So where so that is a phi L1 is a the primary leakage flux, okay, primary the leakage flux of the transformer. So what is the primary leakage flux? It is a small portion of, okay, this is a, so it is the small portion or small part of pi 1 dash, okay, this is a pi 1 dash. Now similarly pi L2 is a, what is the mean by pi L2? So that is the secondary the leakage the flux of transformer. So what about this portion? Okay, it is a small portion of, so it is the small portion or small part of, okay, pi 2 dash, okay, pi. So this is present in the air, okay, through air, okay, these are present in the core, okay, this one is a the present, okay, in this in the primary winding, so through air medium, okay, through the air, so that is a air medium here. So now this is also present, yeah, it is a present, okay, in secondary winding, okay, through air. So this is the exact definition of the leakage flux. All of you clear point? Leakage flux is a load component of the flux. Okay, I have mentioned the load component of flux. Why? Because pi 1 dash and pi 2 comes into the picture under loaded condition. That's why we can say that load component of the flux. So which links either in the primary winding or in the secondary winding, but not links in the both windings of the transformer. So if the flux links in the both winding, it is treated as the mutual flux of the transformers. Okay. Yes, Arun, that's correct. Under no load condition, actually this is the under no load condition, leakage flux is negligibly 0. So here note, under no load condition, okay, phi L almost equal to the 0. There is no leakage flux under load condition. That's why leakage flux in the transformer is treated as the load component of the flux. Pratik, we can find full load current, off load current. Full load means total load is applied on the secondary side of the transformer. Off load means the load current is reduced by 50%. 3/4 load means load current is reduced by 3/4%. Like, समझ गए आपको? What is the mean by leakage flux? This is the question here. What is mean by, what is the leakage flux? Okay. So next, another possibility of the question, see here. So what is the difference between, what is the reason, basic reason to get leakage flux in the transformer? Leakage flux in transformer. Okay, anyone can answer this? Okay, क्या रीजन है, बेसिक रीजन क्या है द लीकेज फ्लक्स आने के लिए इन ट्रांसफॉर्मर? ओके, बताओ अब क्या रीजन है लीकेज फ्लक्स, द लीकेज फ्लक्स इन द ट्रांसफॉर्मर, रीजन क्या है? गुड मॉर्निंग. यस, लोड. द बेसिक रीजन टू गेट द लीकेज फ्लक्स इन द ट्रांसफॉर्मर इज ए लोड करंट. ओके, इफ देर इज नो लोड, डेफिनेटली देर इज नो लीकेज फ्लक्स इन द ट्रांसफॉर्मर. वेरी गुड. अरे इटसेल्फ क्या है? इटसेल्फ मतलब itself, I mentioned that here. So here is a load component of the flux. Okay, under loaded condition these two fluxes are comes into the picture. So under no load condition what will happen? There is no leakage flux, there is no leakage flux. So for example point C, so under no load conditions, okay, this is under the no load, so what will happen? So under no load, so here is a, which flux is present? Only phi 1. Okay, this induces the EMF in the primary winding as well as a secondary winding. So this flux comes into the picture because of the magnetizing current. Okay, so this is the scenery under no load condition. So now under the loaded condition what will happen? Listen. So under loaded condition, So how many fluxes are there? Okay, this is the primary flux pi 1, and in the primary winding pi 1 dash, okay, and secondary flux is the phi 2. So these two are equal and opposite here. Okay, these two are equal and opposite. So now how much here? Practically it is the 99% of the pi 1 dash opposes the 99% of the pi 2 to satisfy the Lenz's law. So remaining 1% of, okay, this the remaining, the 1% of, okay, pi 1 dash, okay, this remaining 1% of pi 1 dash, so present in primary, present in the primary winding of transformers. Okay, this is the present in the primary winding. Now similarly, this remaining 1% of, okay, this is the remaining 1% of the phi 2 present in the secondary winding only, okay, present in the secondary winding. So then what will happen? So this remaining 1% of the pi 1 dash, so is treated as a primary leakage flux pi L1. So this flux is treated as the secondary leakage flux pi L2 here. So what about the total leakage flux? Okay, this is the total, the leakage flux of the transformer. So that is a phi L is equal to phi L1 plus, okay, phi L2 values. So this is the total leakage flux of the trunk. So just imagine there is no load current. The no load current, so there is no phi L1. So that is the phi 2 is equal to 0, phi 1 dash also equal to 0. So therefore phi L1 is equal to 0 and the phi L2 also is equal to the 0 under no load condition. So that what is the basic reason to get the leakage flux in the transformer? The load current is the basic reason, okay, originating point that to produce a leakage flux in the transformers. Okay. Are a clear point? So that the load current, okay, is the basic reason to get leakage flux in transformer. Okay, this is the answer for this question. And next one more question, that is a, so what are the difference between, okay, what are the difference between the leakage flux and the mutual flux? Okay, now tell me, what are the difference between the leakage flux and mutual flux? Can you answer? What are the difference between the leakage flux and mutual flux? Okay, see here. So leakage flux of first one, mutual flux of the transformer is independent of the load current or load variation. Or leakage flux or mutual flux flows in the transformer core. Okay, this is a transformer core which is independent of the, okay, load current and load variations. Okay, but what about the mutual flux? Suppose I have taken, so one side it is the mutual flux of the transformer and other side, so I have taken, so इस तरफ हम leakage flux को लेंगे, here the leakage flux phi L, right, and mutual flux, okay, this is the phi M. So what are the difference between the leakage flux and the mutual flux? So first one, so mutual flux means, okay, which links, okay, it links in, okay, links in the both windings, okay, both, so winding of transformer, okay, this is the winding of transformer, so through transformer core, okay, this is a transformer core here, so this is the first two, and here, so in this case, the leakage flux here, the it links in, okay, it links either in the primary winding, so either in primary winding, okay, so or the secondary winding of transformer. Okay, secondary winding. So the secondary winding through the which medium? So through the air. So through the air. Okay, but not so through the air medium here. So but not in the secondary, but not in the both windings. Okay, but not so in okay both winding of transformers. So if the flux links in the both winding, that is treated as the mutual flux. Okay. So therefore what we conclude here, so total flux in here, that is equal to the mutual flux plus the here leakage flux. So now that's why we can say that okay here leakage flux is equal to the phi L1 plus okay phi L2 here. And second difference is okay this is, so it depends on the which current, magnetizing current. Okay, this magnetizing current that create the mutual flux. Okay, this is so magnetizing current. Okay, magnetizing current. So that is a magnetizing current creates. Okay, this is a create. So mutual flux in transformer. Okay, this is. So now this, that's why we can say that mutual flux is equal to N1. So I mu divided by the reluctancy of the core. So now this one is the load current creates the leakage flux in the transformer. So that is a load current okay creates so leakage flux in transformers. Okay, load current is responsible to produce a leakage flux in the transformers. Now next one, so we have one more. So this the mutual flux. So phi m is independent of the load current or load variation. So load variations here. So as the load increases, so there is no change in the mutual flux. Now this one here, the leakage flux that depends on the load current or the load variations. Okay, this is the load variations. Okay, these are the difference between the leakage flux and the mutual flux of the transformers. Have you got it, my point? Shrutika, why it is not links in the both winding means, suppose, so we have a total 100% of the flux is there. For example, so phi 1 dash is equal to, okay, this is a example point. So that is a pi 1, the pi 1 dash is equal to 100% of the flux and pi 2 also equal to the 100% of the flux. So ideally we can say that, okay, ideally, so 100% of the pi 1 dash opposes, okay, this 100% of the pi 1 dash opposes 100% of the phi 2, okay, to satisfy, okay, Lenz's law, okay, and cancelled each other. Okay, these are cancelled each other here. So but practically what will happen? Okay, these are practically, so that is a, okay, this one is instead of 100%, some amount of the flux present because of the mutual coupling. For example, 100% of, we cannot achieve 100% of the mutual coupling between the two windings. Okay, so it is not mutual coupling here, k is equal to 1, if the k is less than the 1. So if it is a 100% of the mutual coupling between the LV winding and HV winding, definitely leakage flux is that 0, not at all, but it is practically it is not possible. So that here what will happen, practically 99% of the pi 1 dash, okay, opposes, so 99% of the pi 2, so to satisfy the Lenz's law, okay, Lenz's law here. So therefore the cancelled each other, okay, these two fluxes are cancelled each other. So remaining, okay, this one is the remaining 1% of, okay, this is the remaining 1% of pi 1 dash, okay, links in the which winding, okay, this links in the primary winding, and the remaining the 1% of, okay, 1% of the pi 2, the links in the secondary winding of the transformer. So what is the basic reason here why it is not links? That is the mutual coupling is not much strong, okay, as like ideal in case of the practical case. Okay, have you got it now, Shrutika? Okay, so now let's discuss the another part. Listen. So there is another possibility question, that is, how do we represent phi L1 and phi L2 in equivalent circuit of the transformer. Okay, so how do we represent phi L1 and phi L2 in the equivalent circuit of the transformer? So that is how do we model, okay, how do we model the phi L1 and phi L2 in the equivalent circuit of the transformer. Okay, how do we model or how do we represent phi L1 and phi L2 in the equivalent circuit of the transformers part. So see here, the in case of the primary winding, okay, this is the in primary winding of transformer, okay, this is a primary winding. So now what are the present in the primary winding? Okay, primary winding only, okay, this is a primary winding only. So now here is the pi L1 is a present, okay, in the primary winding. So now this is a second one, so that is the number of the turns, okay, here number of turns, okay, so that is equal to N1. So this pi L1 is a time varying nature of the flux, okay, that is a phi maximum, the sin omega t here, okay, this is the primary leakage flux, okay, this one is a primary leakage flux, so which links in the primary winding only here. So already I have mentioned in case of the first class, what are the basic requirement to induce the EMF in a winding. So one is a magnetic field, okay, set of conductors and relay to time variation between the magnetic field and set of conductors. So these are satisfied. There is a flux, okay, conductor hai, flux bhi hai. So this flux is a time varying nature of the flux. So definitely what will happen, some EMF induces in the primary winding. So which EMF here? Some extra EMF. So that, okay, this one is a, so due to phi L1, okay, due to the phi L1, some extra EMF, okay, extra the voltage, okay, extra voltage induce, okay, induced in primary winding, okay, this is a primary winding. So now this is represented, okay, that is a, so therefore that is a voltage, okay, induced, so due to the leakage flux induced in the primary, induced in primary winding, so due to, okay, phi L1, okay, phi L1 here. So it is represented with the EX1. I have represented with EX1 value. So this EX1 is equal to minus N1. So d phi L1 by the dt. Okay, these are d phi L1 by dt. So what is the nature of this here? Okay, this is a, so what is the nature of, okay, nature of the EX1? So this EX1 opposes the applied voltage. Okay, this is a, the EX1 opposes, okay, applied voltage V1. So to satisfy the Lenz law, okay, this is a, to satisfy the Lenz law, so that, so it is treated as the which one here? So it is treated as a voltage drop, okay, voltage drop of the machine. Okay, now similarly, okay, in the secondary winding what will happen? Listen. So in case of the secondary winding, so what? So in secondary winding of transformer, so there is a flux, okay, flux hai secondary winding mein, so through air medium, so kya flux here? So that is a secondary, the leakage flux, okay, this secondary leakage flux, so it is a pi L2. So number of turns bhi hai secondary winding mein, so that is the number of, okay, turns in the secondary winding of transformer. So it is denoted by I2. So A flux be time varying nature of the flux. Okay, so third one is it is also phi L2 is also so phi maximum sin omega t. Okay, this is also time. So due to this phi L2, okay, due to this phi L2, some extra voltage induced in the secondary winding according to Faraday's laws of electromagnetic induction. So here this one is a according to, so which law here? So Faraday's laws of electromagnetic induction. Okay, this one. So according to Faraday's laws of electromagnetic induction, some extra amount of EMF induces in the secondary winding. So that is a, so EX2 values. Okay, due to phi L2. So this is due to phi L2. Okay, some the extra EMF induces. Okay, some the extra EMF. Okay, induce the extra EMF induced in secondary winding. So secondary winding of transformer. So that is represented with the EX2. So that VX2 is equal to, okay, minus N2. So d phi L by, okay, that is a, so differentiation of the secondary leakage flux with respect to the time. So now question is, what is the nature of, okay, this nature of the phi, okay, that is a nature of the EX2. Okay, this one EX2 values here. So nature of the EX2 in the secondary side, okay, E2 is the source. Okay, in the secondary winding, so which is the source? The source voltage. Okay, source voltage is a EMF induced in the secondary winding. So this EX2 opposes the existing EMF. Okay, E2. So therefore EX2 the opposes, okay, the E2 to satisfy, okay, Lenz's law. Okay, so why it is a Lenz opposes here? If there is no E2, no current flows in the secondary winding, there is no current, no leakage flux present in the transformer. So that's why EX2 opposes the E2 to satisfy the Lenz's law. Okay, so this is a, so that, okay, it is the treated as, okay, treated, so as the, what is the treated as a, the voltage drop of the transformers. Okay, voltage drop. Suppose by writing the KVL equation, note, okay, see, so by KVL equation, so we can write, okay, V1 is equal to, so that is the I1 R1, E1 is equal to E1, the plus I1 R1, the plus EX1, okay, EX1 here. So now similarly here also, okay, note, so that is a by KVL in the secondary winding, KVL in the secondary winding of transformer. So how do we write? So that is the E2 is equal to, okay, so this one is a, the V2 plus I2 R2, the plus, okay, EX2 values. Okay, this is the EX2 here. So now what we conclude here? Okay, what is the conclusion in our discussion? So leakage flux in the transformer gives some amount of the voltage drop, but not any power loss. All of you got it point? The leakage flux in the transformer gives some amount of the voltage drop. Okay, voltage drop create होता है leakage flux से, but not any power loss. So that which is the suitable element to represent the voltage drop without any power loss? So if I represent with the resistive element, so definitely there is a power loss. So that the resistance element is not suitable. So which is the suitable element to represent the voltage drop without any power loss? The reactance element is the inductive reactance element is the best suitable element to represent the voltage drop without any power loss. Okay, so that in that what we conclude here. So leakage flux in the transformer. Okay, leakage flux. So in transformer, okay, so creates, okay, some amount of the voltage drop, so but not, okay, but not the power loss. Okay, this is the power loss. So okay, the inductive reactance, okay, this is the inductive, the reactance is a best suitable element. So best the suitable element, okay, element, so to represent voltage drop. Okay, these are to represent the voltage drop, okay, without any power losses, okay. So without the power loss, got it point? That's why, okay, that's why. So what we have to do, okay, so voltage drop, okay, voltage, so drop due to, okay, primary leakage flux. So pi L1 is represented with, so J I1 the X1 drop, okay, this. So voltage drop due to the secondary leakage flux, okay, phi L2. So it is represented with, so that is a EX1, okay. So this is the EX2, so that you can write the JI2 inductive reactance. That's why we have taken as a J. So therefore the KVL equation, so voltage, the equation, the primary winding, so that is equal to, what is the answer? So this is the here V1 is equal to E1 plus, okay, I1 R1 plus JI1 the X1 parameter. So voltage equation in the secondary winding of transformer, so that is the E2 is equal to, okay, V2 plus I2 R2 plus the JI2 the X2 parameters. So where X1, okay, is a X1 and X2 are the leakage reactants, okay, this is one is a the leakage, the reactances in the transformers, okay. So these are, okay, these two are the imaginary elements of the transformers, okay, imaginary the elements, there is no physical appearance. So we have model with the voltage drop, model the voltage drop due to the leakage flux with the inductive elements. That's why these elements are treated as a imaginary elements of transformers, okay. Have we got it? So that's why we have represented with the element of the X1 and X2. Arun, thank you. Manish, thank you very much for your love. आप इतना मोटिवेशन दे दो, मैं बहुत करूँगा मिशंस में. थोड़ा स्ट्रेंथ, लाइव स्ट्रेंथ भी अच्छा होना चाहिए. बस आप अटेंड करो एवरी सेशन. I will make you very good in the missions. No, not at all. See here, Shrutika, actually your question, I know that question. See, the leakage flux is comes into the picture under loaded condition. So next one, mutual flux under no load condition also, there is a small amount of the leakage flux practically, but it is a neglected, okay, it is a very small value. So that neglect. So load current is how much about the load current? It is a rated current, but I know is the only 4 to 6% of the rated current. So this one is due to which very small amount of the leakage flux which is negligible, but flux due to the rated currents, okay, it is a very high. So that's why we cannot neglect this flux. Under no load condition also there is a small amount of the leakage flux, but which is very less because the magnetizing current is only 4 to 6%. But leakage flux comes into the picture because of the rated currents, rated current in the rated current of that or load current of the transformer. So which is very high as compared to magnetizing current. So flux present in these two windings which cannot be neglected. Suppose we have so there is a AC here, this is the primary winding, and this one is the secondary winding of transformer. Okay, flux present in these two windings, okay, through the air medium. So here reluctancy of the core, so definitely is a less as compared to the reluctancy of the air. Suppose we have a circuit like, suppose this one is a, so it is a resistance, okay, 1 ohm, and this one is a the resistance of the 1000 ohms, okay, like this. So what will happen? Okay, this is the resistance is the 1 ohm and it is a 1000 ohm. Suppose here 10 I amps of the current, that is that, so I amount of the current passes through here. So now if this I is equal to, let us assume 10 amps of the current. So this always current chooses the minimum resistance path, always. So that means here is a current is a 9.9 amps, for example point, and this is a 0.1 amps. Okay. Similarly, in the transformer also, so we have a two medium. Okay, one is a, that is a core, transformer core. So now one more medium is a air. Okay, this is the one area. Suppose any flux present here, so this is the air. Okay, this reluctance of this core, okay, reluctancy of the core is a very less as compared to reluctancy of the air. Okay, got it point? So most of the flux chooses the minimum reluctancy path, okay, as like the current, but some amount of the flux passes through the air also. So because of this primary leakage flux pi 1, so this is a very small flux present in the air is a very small, so neglected. Or pi 1 dash and pi 2 is a, so this primary leakage flux pi L1 is a more, okay, that's why we have to consider. What is the reason of the leakage flux? That is the reason. See here, suppose we have a flux pi 1, so definitely flux produced in the primary winding, so which is passes to the transformer core and also air. So but the flux present in the air through the this pi 1 is a very small. So what is the reason? This pi 1 is a the because of magnetizing current. Suppose if I take, so one more pi 1 dash, so this is because of the rated current I1. Okay, this is a rated current. So that's why we can say that. So this the leakage flux pi L1. Okay, this one is the transformer core. So like, so here is a 1% of the flux and this one is a 99%. But here both cases 99%, 99% will be cancelled out. The 1% present in the primary winding. Okay, in primary winding through air. Now similarly in the secondary winding also 1% of the flux present in the secondary winding through air. Now have we got it? Suppose currents, suppose if I take the electrical circuit, one resistance has 1 ohm, other resistance has 10 ohms. So definitely current chooses the minimum resistance path. So here current is a more and this the current is a less. Now similarly in this transformer also there are the two paths. One is a core and other one is a air. So through the core it is a more amount of the flux, in the air very small amount of the flux. So pi L1, otherwise I can say here phi L1 is a, so that is a part of, okay, part of pi 1 dash, okay. So plus, okay, this is a small amount of, okay, this one is part of small part, okay, that is a small part, and small part of pi 1, but this is a comparison point of view, this is very small, okay, very less, okay, very less, so neglected comparison to the this point, okay, this is a very small, so neglected. This pi L1 in the sense actually it is a part of the pi 1 dash, part of the pi 1. Now you got it right, Shrutika? So this pi L1 in the sense small portion of the pi 1 dash, okay, which is present in the air, okay. Now small portion of the pi 1 which is present in the air, okay. So these two are it's treated as a pi L1, but comparisons point of view, this is a more as compared to the pi, this is the this portion. So that's why we can say we can neglected that part. Under no load condition, the leakage flux is negligibly zero. What is the reason? So this is because of the rated current I1. This is because of magnetizing current I2. Okay, I think you got it this point. Why we have neglected here? So pi L1 part of the pi 1 dash, part of the pi 1, but this is a very small as compared to pi 1 dash. This is the primary leakage flux, okay, due to this one. So that's why we can neglect it. The what we conclude finally, the leakage flux in the transformer under no load condition negligibly zero. Right, very good. So next one, how to find x01 and x02. Okay, listen. So how to find the x01, or how do we transfer the, or the another question. So suppose before this we can say that how to transfer reactance parameter, so from one side to other side of the transformer or another side of transformer, okay. So how do we transfer the reactance parameter from one side to another side of the transformer? So we have a question. So in order to transfer the resistance parameter from one side to another side, so what are the conditions to be satisfied? That is copper losses should be maintained constant. Copper losses before transferring equal to the copper losses after the transferring here. Similar way, in order to transfer the reactance parameters, okay, reactance parameter from one side to another side. So what is the condition to be satisfied? The per unit reactance drop, okay, in some element that is equal to the per unit reactance of the transformer in the same element after the transferring, okay. So this is nothing but, so to transfer, what is the condition to be satisfied? So to transfer the reactance parameters, the parameters from one side to another side, from one side to another side of the transformer, so that is a per unit the reactance drop, the drop, okay, drop should be maintained constant, okay, maintain constant here. So what it means, okay, maintained constant, so that means, okay, here the per unit reactance drop, okay, reactance drop, so in some element, okay, in the some element, so before transferring, okay, before transferring is equal to, so per unit reactance drop in some element, so before transferring, so that is equal to the per unit reactance drop, okay, reactance drop, so in the same element, okay, same element, so after the transferring, okay, this is the condition. So to transfer the reactance parameter from one side to another side. So let us take example point. So what will happen? So first one, so from, okay, secondary to, okay, primary side of the transformer. So we are the transferring the reactance parameter So from secondary to the primary side. So let us draw the simplified diagram. Okay, this one is a simplified diagram point of view. So listen. So we have the reactants, okay, primary side, okay, this reactants I can say, okay, x1, okay. So let us, okay, this is the x1. So x1 is a primary leakage reactants and x2 is so this reactants, so I can say x2, okay, these are secondary leakage reactants, okay. So now this side current passes through, okay, here I1 amount of the current, okay, this current is that is I2 current, okay, this one. So here primary side of the transformer, so EMF induces in the primary winding E1 and this one is the secondary side of the transformer, so EMF induces in the secondary winding, okay, E2. So now we are transferring the reactance parameter, okay, this x2, so from here secondary to the primary side. After the transferring, it is denoted by the x2 dash, okay, x2 dash here. So this is the before transferring, so this one is a before transferring and this one is after the transferring, okay, AT-BT, AT means after the transferring, before transferring here. So let assume here, okay, let x2 is the leakage reactants in the secondary winding, okay, reactants, so in secondary winding of transformer, so before transferring. Similarly, let the x2 dash in the sense the reactants in the secondary winding after the transferring. Now what is the condition to transfer the reactance parameter from one side to another side? So now tell me the condition. So that is a per unit reactance, okay, of the per unit reactance. So before transferring is equal to per unit reactance after the transferring. So which is the actual element? So per unit reactance, how do we find out? Very simple technique, no need to find out base, kVA, all these things. So just actual value is what? Okay, x2 dash, okay, x2, okay, actual value is x2. So now here secondary side, so base value in the sense, okay, it is a E2 base voltage by the base current, okay, secondary side, okay, this is the before transferring. So this one is, you can say that, so actual value in the ohms, okay, this is the base value in the ohms, okay. Similarly, so now after the transferring, actual value is a x2 dash, okay, what is the base value here? So this is the actual value divided by, so base value, okay, this one you can say that, so current is which current flows, okay, base voltage E1 by, so I1, okay, base voltage by base current. So now simplify this, okay, this is the actual value, so by base values here. So therefore here I2 x2 divided by E2 is equal to, so that is the I1 x2 dash divided by E1. So we required x2 dash, okay, let us find out. So x2 dash is equal to, what is the value of x2 dash? Now tell me here, so it is a E1 by E2, okay. So I2 by I1 multiplied by, so that is a x2 values, E1 by E2 in the means, so it is equal to 1 by k. So here 1 by k, so into x2, so that therefore it is equal to x2 by k square, okay, x2 by k square. So now here the x02, okay, x01. So let us assume x01 is the total reactance, okay, reactance, the refer to primary side, okay, these are refer to the primary side. So that is equal to, what is answer? x1 plus, okay, x2 dash. So x1 plus x2 by k square, okay, this is the reactance, the refer to the primary side. Similarly, let us take one more example. So that is the second one. So from primary to, okay, this is the primary to the secondary side of the transformers. So we are transferring the reactance parameter from primary to the secondary side. So पहले हम क्या करेंगे? The single line diagram ड्रा करेंगे इधर. So देखो आप ध्यान से देखो, आपको easy रहेगा. So this one is okay, primary side. So we have a leakage reactance. A हमारा leakage reactance in the primary winding. So now this is a x1. Clear my point? So now here current passes through the here I1 amount of the current. So the primary induced EMF, okay, it is a E1 primary induced. So now secondary side, okay, reactance क्या होगा? So secondary reactance is existing secondary reactance is the X2, okay. So now current passes through the here I2. So here secondary side, okay, secondary winding EMF induces here the E2 values. So now we are transferring, okay, this reactance, so from primary to the secondary side, okay, here. So this is the X2 dash. You can connect here also, there is no problem. So I am per our this diagram is just like single line diagram, okay. So now by using this, you can say that let X1 is nothing but what, okay, X1 is the reactance in the primary winding, okay, in the primary winding. So before transferring, okay, before transfer. So now X2 is X1 dash is the reactance in the primary winding after the transferring. So now what is the condition to transfer the reactance parameter one side to another side? So per unit reactance, okay, per unit reactance, the before transferring, okay, that is equal to the per unit reactance, okay, of the transformer. So after the transferring. So which is the actual element, okay, before transferring? X1. So therefore you can write directly. So I1 X1 by the E1, okay. So now this is equal to I2 X2, okay, I2 X2 dash by the E2. You can write actual value is X1. So base values in the primary winding, base voltage by base current. Actual value is X2 dash, base voltage by base current in the secondary side. So this is the per unit reactance before transferring, per unit reactance after the transferring. Now simplify, okay, we will get the X2 dash, okay, therefore X2 dash is equal to, so that is the I1 by I2, okay, divided by, so E2 by E1, so that is equal to X1, sorry, this one is a X1 dash, right. So X1 dash, okay, that is equal to, so now simplify here 1 by K, the into 1 by K, okay, into X1. So now there, okay, it is a 1 by K or 1 K value, sorry, so listen, the I1 by I2 is a 1 K and multiplied by X1, that is a K square, the X1 values. So now therefore, so that is a X02 is a total reactance, okay, this is a reactance of transformer refer to which side? The secondary side of the transformer. So this value X02 is equal to existing reactance is the X2 and transferred reactance, okay, that is equal to X1 dash. So this value is equal to, what is the answer? The X2 is equal to X2 plus, okay, the K square X2 plus the K square X1 values, okay. This is a complete the reactance parameter refer to the secondary side, and this is the reactance parameter refer to the total reactance, so refer to the secondary, this is the X01. So this is the reactance refer to the primary side of the transformers, okay. All of you got it? Like this we have to calculate all the parameters. First one, what is the mean by leakage flux, originating point, differences, how do we model the leakage flux in the equivalent circuit, and how do we transfer the reactance parameter from one side to another side. Leakage flux occur in the both winding and both winding, but not links in both winding. Shrutika, the leakage flux occurs in the both windings, definitely in primary and secondary, but not links in the both winding. That is the difference. Shrutika mentioned that, so sentence should be the leakage flux occurs in the both winding, primary and secondary. Yes, that's correct. The leakage flux occurs in the primary winding and secondary winding, but not links in the both windings. leakage flux present in the primary winding and secondary winding, there is no doubt at all, but which is not links in the both windings. Common wind, there is no common path for both windings. So for mutual flux there is a common path through the transformer core. So that's why mutual flux which links in the both windings. But in the leakage flux there is no common path for both windings. Now have you got it? So now let us solve this question, all of you. A 50 Hz 5 kVA 400 upon 200 volts transformer has leakage reactance of 4 ohms and 0.04 ohms in primary winding and secondary winding respectively. So total reactance of the transformer referred to the primary side, total reactance of the transformer referred to the secondary side. So now here is a find out following. So find out following. Okay, so first question number 1. So total reactance of the transformer referred to the primary side, total reactance of the transformer, the reactance of transformer referred to the secondary side, total reactance of the transformer per unit reactance referred to the primary side, per unit reactance referred to the secondary side, percentage reactance referred to the primary side, percentage reactance referred to the secondary side. This is our question. Okay, I will solve first question. Suppose it is a given rating that is a 5 kVA, okay, 400 upon 200 volts transformer. So from here we can find out, okay, that is a, so we can find, so this is a 400 by 200, so therefore K is equal to the E2 by E1, so that is equal to, what is the answer? Okay, 200 divided by 400, so it is equal to 0.5. Okay, so next one, let us find out primary current. So that is a VA rating of transformer. Okay, VA rating, so divided by EMF induces in the primary winding. So that is equal to 5 into 10 to the power of 3 divided by, so 400. Okay, it is always, okay, E1 by E2 only. Okay, E1 by E2. So now that is equal to how much? Okay, it is a 12.5 amps. So 12.5 amps, got it? So next one, let us calculate secondary current. So that is a VA rating of transformer, okay, divided by, so EMF induces in the secondary winding. So that is equal to 5 into 10 to the power of 3 divided by the 200. So equal to the 25 amps. Okay, this data is required to find out. So question number 1. So first let us calculate, okay, question number 1. So what is the formula here? Total reactance of the transformer referred to the primary side. So how do we get this reactance? Okay, X01. So X01 in the means, okay, so existing reactance, okay, X1, the plus, okay, so existing reactance plus that is a X2 dash, okay, that is equal to X1 plus the X2 by K square. Now simplify this, the X1 given, okay, that is a X1, so is equal to 4 ohms and X2 is equal to 0.04 ohms. So now substitute here, so that is a X1 is equal to 4 plus 0.04 divided by 0.5 square. Now what is the answer for this question? Calculate. So this part 0.04 divided by 0.5 square plus 4. Okay, this is equal to 4.16 ohms. Okay, now similarly let us calculate second question. So that is the X02. Okay, what is the formula to find out X02? So that is the X2 existing reactants plus the X1 dash. Okay, X1. So X2 plus, okay, K square X1. So this is, so X2 is equal to 0.04, the plus, okay, here K square is equal to 0.5 square, the into X1, okay, X1 value is a 4. So now simplify, you will get answer. So what is the answer? Anyone calculated? Sir, what is K here? K is the transformation ratio, right? Okay, K is equal to 200 upon by 400. K in the sense transformation ratio. Transformation, okay, ratio of transformer. Okay, that is equal to E2 by E1. So this is the E2 and this one is the E1, so that 0.5. So now calculate this part. So it is equal to 1.04 ohms. You also calculate and let's verify whether it is a correct or not. Okay, so next question number 3. So here, so what is the question number 3? That is the per unit the reactancy of the transformer. Okay, per unit the reactance of transformer refer to which side? The refer to the primary side of the transformer. Okay, primary side. So that is equal to, okay, we can write. So which is the actual value here? The actual value is the X01. Okay, this is the actual value. So what are the base actual value in the ohms, right? Okay, this is the base voltage in the primary side. Okay, E1 by the I1. So this is also in the ohms. So now simplify this. Okay, it is equal to I1. So it is the actual value divided in the ohms, base value also in the ohms. So that it is the X1 I01 by, so E1. Okay, it is no need to find out all these things. Directly you can find out X01 actual value, base value in the primary side, voltage by current. Okay, that is equal to I1 X01 by E1. So now calculate. So I1 already we have calculated 12.5. Okay, so this I1 value, and X01 is equal to, so 4.16, okay, divided by, so this E1 is equal to 400. So now find out this answer. What is the answer for this question? Yes, so that is the 0.13 per unit. 0.13, very good, that's correct. So next one, calculate another one. So fourth one is the per unit reactancy of the transformer. Okay, reactancy of transformer. So refer to, okay, secondary side. First, how do we get the formula? So here refer to secondary side, total reactance refer to the secondary side. So that is the X02. Okay, it is in the ohms, right? So which is actual value, okay, divided by. So secondary side base value here, base voltage in the secondary side. So base current in the secondary side, which is also in the ohms. So actual value in the some units divided by base value in the some units. Okay, got it? So now simplify this. Okay, it is equal to, so I2 directly you can write. So for our Understanding, I am writing this step. Otherwise, you can write directly also. I2 X02 divided by the E2. Okay, this is the formula. So, per unit reactance refer to the secondary side. So, now calculate. So, what is the I2 value? So, I2 is equal to, so this is the 25 amps. So, now X0 is 1.04. So, E2 is equal to 200. So, now this tell me what is the answer here. It is also, is it what 0.13? Check it once. Yes, so that's 0.13 per unit. So that is our per unit remains same. Okay. So next one, let us calculate the percentage. So that is the fifth one. So that is the percentage, the reactancy of the transformer. Okay, reactance of transformer refer to primary side. Okay, refer to the primary side. So that is equal to, so per unit reactance of the transformer refer to the primary side multiplied by 100. So 0.13 into 100. So that equal to the 13%. Okay. So next, the fifth question, how do we get? So percentage reactance of the transformer. Okay. Reactance refer to, okay, secondary side of the transformer. So similar, this is also equal to per unit reactance, the refer to the secondary side into 100. So that the 0.13, okay, into 100, so it is equal to 13%. Okay, got it? Yes, very good. That is equal to 13%. So now what are the observations from this problem? See, first observation here. So very important exam point of view, listen. So what are observations? Okay, first observation is so first one, the per unit reactance refer to the primary side. So refer to primary side, the is equal to, this is the per unit reactance of the transformer, the refer to primary side. So that is equal to the per unit reactance of the transformer, the refer to secondary side. Okay, this is the one of the question in competitive exam. Now similarly, second one, the percentage reactance of the transformer, the refer to primary side. Okay, that is equal to the percentage reactance of the transformer, the refer to secondary side of the transformer. Okay, so these two formulas are very important for exams point of view. So we can expect the question from here. Okay, have we got it? So now let's solve this question. A single phase, okay, 2400 upon 240 volts transformer has following winding resistance and reactance in the ohms. So where R1 is equal to 0.5, R2 is equal to 0.051 ohm, and X1 is equal to 4 ohms, X2 is equal to 0.04 ohms. The secondary is connected to the load. Okay, this secondary is so connected to the load having the resistance of the 4 ohms and reactance of the 3 ohms. Determine the following. So we are transferring the all parameters from secondary to the primary to the secondary side. So if you draw the equivalent circuit like this, suppose we have a secondary induced EMF, okay, E2, okay, this is the secondary induced EMF, and resistance refer to the secondary side. So that is a R02, and reactance refer to the secondary side X02, and current passes through here I2 current. Okay, so now this is the I2 here, and load resistance oka RL and load reactance XL. Okay, this RL line, the XL value. So this value is given. So now find out, okay, here. So which is the, this part is a load, okay, here load, and this is the terminal voltage, the load terminal voltage, the V2. Okay, so we have to find out the I2 current. Okay, next one, the load power factor, secondary terminal voltage, and power consumed by the load. Okay, so these are the questions in this case. So now calculate first R02 and X02. Okay, what about the K value here? So given rating is a rating of the transformer is equal to voltage rating. So that is a, okay, voltage, the rating of transformer. So that is 2400 upon 240 volts. Okay, 240 volt. So it is always E1 upon, okay, E2 only. Okay, always EMF induced in the primary winding to secondary winding. So now from here you can get sorry, the K is equal to, okay, EMF induced in the secondary winding. So E2 by E1. So E2 is equal to 240 by, so 2400, so that it is equal to 0.1. So by using, okay, this is there. Next let us calculate the R02, okay, R02 values. So how do we get R02? R02 is equal to existing resistance plus transferred reactant. So R2 plus R1 dash, so that is the R2 plus, okay, K square R1. So now substitute here, what is the value of R1? So R1, R2 is equal to 0. Okay, so 0.1 plus, so what about R1 value? Okay, K square is equal to the 0.1 square into 0.5. Okay, so now find out R02. R02 values. So this value is equal to 0.015 ohms. Okay, this is the R02, and the X02, let us calculate X02. So that is a X2 plus, okay, X1 dash. What is the value of X02? X2 plus X1 dash. So X2 is equal to 0.04, okay, 04. So plus K square, okay, K is equal to 0.1. This is the, so X2 plus K square X1. So now this value is equal to, so K square X1 value, X1, so that X2 equal to 0.04, okay, plus X1 is a 4. So now it is a, the 0.1 square into 4. So now calculate, okay, this value. You have to calculate, and please comment in the comment box whether it is a correct or not. We have to, calculation part is yourself. I will tell you how to solve the question, but calculation you must calculate yourself. Otherwise we don't have, if we don't have a practice to calculate the questions, in the exam definitely will do mistake. So practice the calculation part also. Yes, this is equal to 0.08 ohms. Very good. So Shrutika, you got it? Yes. No, 0.8 is not correct. आप करना है अच्छे से, कैलकुलेशन पार्ट आप करना है. अगर कैलकुलेशन को आपको मालूम नहीं तो ना एग्जाम में बहुत दिक्कत हो जाएगा आपको. Okay, So now calculate, suppose we know this part. So it is equal to, see, this one is equal to the 0.015 ohms, and X02 is equal to, okay, the 0.08 ohms, and RL load resistance is equal to, okay, it is a load resistance. So this one is a 4 ohms, and this one is a, okay, 5, okay, it is XL is equal to how much? So that is the reactance is the 3 ohms, okay, this value is given. So first question we have to find out load current, okay, load current, let us calculate load. So we can find out the load current, okay, load current. So I2 is equal to, so that is a EMF induces, okay, E2, okay, divided by, okay, V2, and it is a R02 plus R2, sorry, R02 plus RL, so plus J X02, okay, plus, so X02 plus XL values, okay, XL. So now what is the E2 value? Okay, E2 is a 240 volts. So now they simplify here. So E2 is a 240 at an angle of the 0. So divided by R02 is equal to, so how much, what is the R02? 0. So 0.015, okay, so plus, okay, 4, okay, divide the, that is the plus J, so 0.08, so plus, okay, 3, okay, this is a 0.0. So now simplify this, okay, this value is equal to, we can write, so 0.04 and all the values. So now simplify, okay, it is equal to, so 240 at an angle of the 0, okay. So now this one, the 4 point, okay, so 4.015 plus J, so 3.08, okay. So now convert into the polar form, this one calculate. Okay, suppose, so it is a polar form is required. So what is answer? This one. Have we got it? Okay, 47.428. 47 or 37? Are clear my point? .015, so 3.08, right? So it is equal to the 240 at an angle of the 0 divided by, so this part we can convert into the polar form, okay. So that is a 5. Okay, 06, okay, 02, okay, 0602, the at an angle of, okay, 37 point, so 37.492 degrees, okay. So now convert, okay, into this part. So now simplify here, all of you simplify and calculate, okay, don't do mistakes, okay, it takes time, but that don't do the mistakes here. So that is a 240 okay, 240 divided by 5.0602. So that is a 47.428 at an angle of minus 37.492. Okay, this is the 37.492 values. So from here we can find out, okay, see the magnitude of, okay, it is the magnitude of the load current. Okay, that is the question number 1. So load current, so that is a I2 magnitude is equal to, so 47 point, okay, it is a 47.428 okay amps. So now second question is power factor, okay, that is a load power factor. So how do we get, okay, it is represent the I2 and this represent the angle theta 2. So therefore cos of the theta 2. So therefore cos of, so 37.492. So now simplify this cos of 37.492. Okay, cos of 37.492. So it is equal to 0.824, the which power factor? Lagging power factor. This minus sign indicates the lagging. Yes, total current and 37. Shrutika, you got it right. Power factor is equal to SS 37, right? Okay, it's I written wrong. Cos of 37.42. Yes, the 0.793 lag. So this is the power factors. So next third question is what? So secondary terminal voltage. What is the secondary terminal voltage? So that is the secondary, the terminal voltage, okay, voltage. How do we get secondary terminal voltage? So it is equal to V2. So V2 is a, so I2 multiplied by the here total impedance. I2 multiplied by the ZL. Okay, ZL here. So V2 is equal to I2 multiplied by ZL. So I2 is equal to, okay, 47.428 at an angle of minus 37.492, okay, into, so this ZL is equal to 4 plus, okay, J3, okay, 4 plus J3 1. So now convert the multiplied here, you will get an answer. Okay, so convert and tell me. First, that is a convert into the polar form. So that is it is a 47.428 at an angle of, So minus 37.492. So this is the here the phi at an angle of, okay, phi at an angle of 36.86 degrees. Okay, 36.86 degrees here. So now calculate sum of these two, okay, multiplied and angle here sum. So now this is a 47 into 0.428 at an multiplied by 5. So it is equal to 237.14. So now angle is 37.492 36.86. Okay, minus, so 0.632. Okay, right. But magnitude of the terminal voltage, that is the 237.14 volts. Okay, this is the terminal voltage. And sometimes we have a question, power delivered to the load. Okay, fourth one is power consumed by the load. So power consumed by load. By load, how do we get power consumed by the load? So I square RL. Okay, I square, magnitude of the I square and RL values. Yes, that's correct. Now find out power consumed by the load. So Ram Prakash Avasthi, sir, I am GATE 2025 aspirant. Can I attend this class? Yes, you can attend this class. In the GATE 2025, you will be the first ranker if you attend this class from onwards. Definitely you can attend. I hope I will see you in first ranker in GATE 2025. Okay, now find out what is the I2 here. I2 already we have calculated. So that I2 current is equal to 47.428. So 47.428 square, the RL is equal to 4. Okay, calculate. So you will get the power. Okay. So what is the answer for this question? Okay, so this is the 8.997 kilowatts. Yes, that's in the watts, that is a 8000 exactly one, sir. Suppose in the kilowatts, this one. That's correct. 888. Yes, that is 8.997 kilowatts. Very good. All of you got correct answers. And next, solve this question. The following figure shows the connections of ideal transformer with primary to the secondary turns ratio of 1:10, 1:100. The applied primary voltage is 100 volts, 50 hertz AC. The RMS of the current. Okay, suppose we required the current. How do we get the current here? Just so transfer this reactance parameter, okay, reactance from secondary to the primary side, and also transfer this reactance from secondary to the primary side. So you will get one equivalent circuit. Find out the current and you just by KVL equation apply the current equation, you will get an answer. So now after the here, so simply write, see, so after transferring, listen, after the transferring the resistance and the reactance, XT reactance from secondary to, okay, secondary to the primary side. So this equivalent circuit as follows. Okay, as follows. Okay, so now the reactance is the existing reactance similarly same. So this is the reactance. So this XL is equal to how much? The 10 ohms, right? So now after the transferring, all are connected in series with. So after the transferring, this will become, okay, R dash, okay, R dash value. So now next one, the capacitive reactance. So this one is a capacitive reactance. So this is a, sorry, it's not inductive reactance. So this is the capacitive reactance I have taken. So that is the XC dash. Okay. Now here the voltage, applied voltage, the V is equal to, so V1, so that is the 100 volts. So we don't know the primary current. Okay. This we have to find out. So it is the R dash. Okay. So how do we get this R dash? R dash is equal to R by the K square. Okay. So now XC is equal to, okay, XC by the K square. The XC is equal to the XC by K square. Now simplify here, the what is the value of the K? So where K is equal to, we got, okay, here, this is the K. So that is the K is equal to N2 by N1. So that is equal to 100 by 1. So that it is a 100. The K is equal to 100. So now simplify. So what is the answers? So where R is equal to 80 kilo ohms. Okay, this is the 80 kilo ohms. Okay, 8 into 10 to the power of 3. So that is a 100 square. Okay. So now XC is equal to, so that is a 40 kilo ohms. So 40 into 10 to the power of 3. So divided by, okay, 100 square. So now simplify. So this one. So it is a, so 10 to the power of 3, here 10 to the power of 4. So that it is equal to, so 8 ohms, and here also, so it is a 4 ohms. Okay, right. So 4 XC values. Now calculate. So complete this reactance. So therefore find out. So apply. So from KVL equation, okay, equation. So we get the primary current I1. So primary current of the transformer I1. So how do we get primary current? Voltage divided by impedance. Okay, voltage divided by, so total impedance, right? Okay, total impedance. So now let us, the impedance here, so that is the V1 divided by, so R dash plus, okay, XL dash. So J XL dash, sorry, XL dash, the plus, okay, it is not XL dash, it is the directly XL only. So J XL, the minus J XC dash. Capacitive reactance, that's why we have to take minus J. So inductive reactance, it is a plus J. So now simplify here. So V1 is equal to how much? So 100 at an angle of the 0. Okay. R dash is equal to 8. Okay. Plus, So now this is the 10 ohms, okay, is it correct? So it is the 10 ohms, okay, J10, okay, minus the J4, so minus Z4. So now this is equal to, so here 100 at an angle of the 0 divided by, so 8 plus, okay, J6. So now calculate this value, 8 plus J6. So this value is equal to 100 at an angle of the 0 divided by 10 at an angle of, okay, at an angle of the 36.86 degrees. Okay, so therefore, so this I1 current is equal to the 10 at an angle of minus 36.86 degrees. Okay, so magnitude of the primary current. Okay, we required only magnitude of the primary current of the transformers. So here find out the RMS value of the primary current in amperes. So what is the answer for this question? So this is the magnitude of primary current. Okay, magnitude of the primary current. So that is equal to 10 amps. Suppose in the same question, so if it is asked the primary power factors, suppose let us, we have to find out, so extra question, that is, so find the primary power factor of the transformer. Okay, this type of the question is given. So how do we calculate primary power factor of the transformer? So primary power factor is equal to, okay, this primary, the power factor of transformer, so that is equal to cos theta 1. So this is the theta 1, okay, it represents the theta 1 and this indicates the magnitude of the I1. So now primary power factor is equal to cos of 36.86 degrees, it is equal to 86. So that is a, okay, 0.8 lagging power factors. Yes, 10 angle minus 36.86. Okay, have we got it, everyone? Okay, so now let's solve one more question based on this concept. See here, this is also similar question. So we have to transfer, that is the consider the transformer shown in the figure. So find the primary current and the secondary current. Okay, primary and secondary currents. So how do we here? So just transfer this one, okay, from the secondary to, okay, secondary to the primary side. Okay. So after the transferring, what will happen? So this equivalent circuit shown like this. So that is the impedance, the first one, source voltage. So it is a 200 volts, okay, 50 hertz. Okay, the primary side, the resistance, okay, it is a 4 ohms, okay, it is a 4 ohms, and this is the capacitive reactance, okay, this is the XC is equal to, so this is the XC value, so that is the XC is equal to 2 ohms, okay, minus J 2 ohms we have to take. So now that is the XC values, and we have, this is the exactly in the primary side. So we are transferring this one, okay, this one we can say, So it is a load, okay, it is a, we can say that ZL dash, okay, ZL dash. So this ZL dash means ZL by the K square, okay, K square. So what is the ZL is equal to here, okay, 2 plus, okay, J2, okay, divided by K square. So where K is equal to, okay, what is the value of the K? So K is a transformation ratio, that is a N2 by N1. So it is equal to 1 by 2. So now substitute here. So this is equal to 2 plus J2 divided by, so 1 by 2 whole square. Okay, then what will happen? So this is a, okay, 2 plus J2 divided by 1 by 4, so that it is a 8 plus J8, the 8 ohms. So now find out current. First one, primary current here. So therefore primary current is equal to, okay, primary current. So that is a, just apply the KVL here. So by KVL equation, so KVL in this loop, okay. So primary current I1, so that is equal to, so voltage divided by total impedance, okay, voltage, so divided by total impedance, okay, total impedance here. So now what is the total impedance here? So that is a V1, okay, V1. So at an angle of that 0 divided by, so total impedance means, okay, it is a, the R, okay, it is a 4 plus 4 minus J2 ohms, okay, J2 plus, okay, 8 plus J8, okay, this is the total impedance. So other, this one is a, otherwise, okay, it is a R, the plus, okay, this is the XC, okay, the, this one is the XC values, the plus, okay, here ZL dash. Now simplify here. So that is equal to 200, okay, at an angle of the 0 divided by, so 4 plus, okay, minus J, the here reactance is the J2. So now this is the plus 8, okay, plus J8. So this is equal to, so 200 at an angle of the 0 divided by, so now it is a 4, okay, minus 4 plus J6, okay, is it correct? No, convert in the calculator. Otherwise, suppose if you want to find out magnitude here, the, suppose here is a plus JB is there. So how do we get magnitude? Okay, magnitude is equal to, so that is the under root of A square plus B square. So now next angle we can find out, that is a tan inverse of, so that is a B by A. Okay, here converting polar to the here, this one. But convert directly in the calculator also, or otherwise magnitude is equal to under root of A square plus BC, and theta is equal to tan inverse B by A. Okay, is it correct? So this is equal to the 200 at an angle of the 0 divided by, so convert into the polar form. So it is a R, this magnitude is equal to 7.2211. So 11, okay, this that 7.2211 at an angle of, so minus 56 point, sorry, the at an angle of, so this is a 56.309. Okay, 309 degrees. 56 or 26? Okay, this is the 8 plus 10 minus J6, right? Sorry, I have taken wrong. So here the real terms, okay, it is equal to, so 12 minus J plus J6, right? That's correct. So that's correct. Yes, yes. Yes, that's correct. 12 plus J6. Now calculate. Convert into the polar. So 12 and this one is the 6. So that it is equal to 13.41 at an angle of 26.56 degrees. That's correct. 26.56. So now simplify here. I1 is equal to primary current I1. So that is equal to, so that is the 200 divided by 13.41. Okay, it is equal to 14.914 minus 26.56 degrees. Suppose here also if you want to find out the primary power factor, suppose question is asked, find primary power factor of the transformer. So that is equal to how much? So it is the theta 1 and it is the magnitude of I1. So that is the cos theta 1. So find out cos theta 1. So cos of 26.56. So this is equal to 0.89 lakh. Okay, it is the primary power factor. But question is that this is the only first question. Suppose second question here, secondary the current. So how do we get secondary current? Okay, we know that the secondary current here, so that is the we know, so K is equal to how much? The K is so I1 by I2, right? So I1 by I2. So where I2 is equal to, we can find out, so K. So that is the I2 is equal to the I1 by the K. So I1 is equal to, so this current, so 14.914 at an angle of minus 26.56. So now this is what is the answer? Okay. So now answer is 14.914 divided by K. So K we got, what is the value of the K here? Already we have calculated. So K is equal to 1 by 2. 1 by 2 here. So that it is equal to 14.914, sorry. Into 2, okay, 29.828 at an angle of minus 26.56 degrees. Yes, that's correct. So this is the all the problems based on this concept. So we have a four possibility of the question. One possibility of the question is transferring the secondary to the primary side. Okay, the question about input current and input power factor. And another possibility is transferring the primary to the secondary side, the output current or secondary current and output power factor. These are the only two possibility of the question here. समझ गए आपको मैं क्या बोल रहा हूं? We have a two possibility of the question. One is a transferring primary to the secondary or secondary to the primary. Question about the input power factor, input current, output power factor, output current. ओके सो कल हम डिस्कस करेंगे इक्विवेलेंट सर्किट ऑफ द प्रैक्टिकल ट्रांसफार्मर. So and also we will solve some questions, some very important questions based on the equivalent circuit of the transformers. So equivalent circuit of two winding transformer, equivalent circuit of the three winding transformer, equivalent circuit of the four winding transformer, like equivalent circuit of the n winding transformer. So that part also we will discuss tomorrow. Okay, thank you all, thank you very much. We'll meet in the evening and discuss about DC machine class, that today evening at 8 p.m. Every day evening 8 p.m. DC machine class and morning 11 a.m. transformer class. अभी सिंगल पेज ट्रांसफार्मर डिस्कस कर रहा हूं. सो सिंगल पेज के बाद 3 फेज ट्रांसफार्मर भी डिस्कस करूंगा. थोड़ा टाइम लगेगा. Quantin Rusty Boyne, definitely I will discuss 3 phase transformer, but it takes some time. Now we are discussing about the single phase, and after that we will discuss auto transformer, then after we will discuss about the 3 phase transformers. Thank you Manish. Okay, so thank you all, thank you very much. We'll meet in the evening. Bye.